How big is big? When we say something's infinite, how much bigger than finite? We have a way of measuring when things are finite, right? If I have 6 apples versus 4 apples, the guy with 6 has more, right? You know, for finite we have a very careful language to say when something's bigger. Some people say that's what math is about. I think maybe that's what arithmetic is all about. Like you say, if we had a hotel room, it was full, someone comes, knocks on the door, says, "Get a room for me." Sorry, it's full. We'll get back to this later. I should say, it's not a joke. Reminds me of this. There's 3 kinds of mathematicians: those who know how to count, and those who don't. I was reminded of a friend of mine who said one day at the club, there are 2 kinds of people: those who think there are 2 kinds of people, and those who don't. I am among the latter, and thought he was incredibly clever. Anyway, so people say, so we don't have a word, or at least actually maybe most of us don't have a word for infinity. Just means not finite. But we'll see. Are there grades of infinity? Hopefully we can answer that before the end of the day. So I'll tell you first the story of this tribe, or pair of tribes. One was watching the other and said, those guys don't have a word for 4. They count 1, 2, 3, many. We're kind of like that too, in that we don't have words for infinity or not. There's awkward. So this one tribe was watching the guys who don't have a word for 4. I said, oh, would you like to trade many apples for many oranges? You could do a fair trade. The other guys are like, sure, apples are worth about the price of oranges. And so those guys went and bought 5 apples, expected to come back with 40 oranges. But the people who didn't have a word for 4, even though they didn't have a word for 4, they said, oh, you brought many apples? We'll bring you, say they brought 5 apples. We'll trade you many apples, and they lined them up. And we'll say that. We'll say 2. So even though they don't have a word for 4, they can still do transactions without getting taken advantage of. And we'll use the same definition for infinite sets, because we're kind of in the same boat. Even though you may say these people are very unsophisticated, it's funny, almost any group of people, almost any culture, they develop a language for numbers. Some cultures have some words for this things are very fine differences between variants, but almost every culture develops a counting scheme. So maybe we'll say 2 sets have the same size if we can line them in a 1-to-1 fashion so that nothing is okay. Maybe you think this. You have your set A, A1, A2, and you have B, B1, B2. And everything gets matched up. Everything gets matched up to one and only one element in the other set, and nothing is unpaired. Maybe you could say. So if it say is, actually what infinite sets can you think of? Can you think of any infinite sets? None. Maybe we could say is, maybe we'll say recall. Remember the first day we talked about n, those are natural numbers, that's 1, 2, 3, etc. Maybe we could say we talked about z. What was z? Z was equal to all that with 0, 1, 2, and minus 1, minus 2. Remember why we called it z? I'm sorry, do you remember why it is called z? they already used n. N was for number. Z is the word for number, or Z is the first letter in the word for number in German, which is Zaun. What were some other sets? We had Q, which was A over B, such that A and B are in Z, and B is not 0. Maybe we could say we had 0, 1, which was the set X, such that X is between 0 and 1. What do you think? Did it all seem the same? Maybe also we have R. We had R in too. A whole bunch more, right? All those sets are infinite. Infinite just means not finite, right? All those sets are infinite. I mean, they're actually getting bigger, right? This set's bigger, this set's bigger. Let's throw this one in. N union 0 for our examples. That's equal to 2. That's just n, or the natural numbers, with one more thing, 0. So it seems like, you know, the sets are getting bigger. This set seems bigger than this set seems bigger than this set definitely seems bigger than everything else. This seems bigger. But let's see. First we'll note the size of the natural numbers is equal to the size of the natural numbers with 0. Why is that? Well, I could line them up. I could say 1, 2, 3, 4, blah, 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 blah. Line up with 1, 2, 3, etc. Everything's matched to 1 and one thing in the other set, and nothing's left unmatched. Maybe if you use the language you used in pre-calculus, you'd say, oh, there's a one-to-one and onto function from one set to another. One-to-one means everything's paired with one and one thing. Onto means nothing in the second set is left unpaired. And since it's a function, everything in the first set goes to something, right? Remember, I was telling someone, I shouldn't talk about this now, but I was telling someone, I was like, yeah, math was always my favorite class. But definitely when I took a class which is similar to what they teach in pre-calculus, my interest went down. Definitely, I was just like, it used to be so good. Like, I remember I got annoyed when I took geometry, because geometry, it felt like talking to a lawyer. Oh, no, you didn't spell this postulate right. Oh, no, you have to say comma here. Oh, no. And I used to get 100 on almost everything in algebra. So I was annoyed in geometry. I still liked it, but I was annoyed. Should I tell you another story? I'm so arrogant, but I can't resist. One time in geometry class, I even fell asleep. And I woke up and the teacher couldn't do the problem. And I told her, just do this and this. She said, oh, yeah, that's good. I'll give you extra credit. Anyway. But actually I should finish the story. But after that, after my pre-calculus year, or algebra and trigonometry type year, I took a calculus and a discrete math class. This was in high school. And I liked it a lot more. And none of my other classes even came close. I mean, I think if they taught philosophy, maybe we would have liked that. And when I took psychology, definitely took psychology, it seemed really interesting. But history didn't seem that interesting. I liked English in that I liked the stories, but when they said you have to write about it, I was like, I just want to talk about it. Anyway, anyone else want to share some stories? You're going to say, come on, the clock is ticking. So here, we're saying, anyone else want to share stories? Is math your favorite subject? It always was. This is another time I'll talk about why I ended up majoring in that. But anyway, so here, these two sets, and it should seem like somewhat surprising. This set has more guys. This has one more thing in it than this. But they have the same size. And we can say, well, what's the story with n and z, the integers and the natural numbers? Do they have the same size? I don't know. First I'll say I'll line up the first one. All right, 1, 2, 3, well, here I'll write 0, 1, minus 1, 2, minus 2. I should make sure the whole goes there, goes there. 4 goes to 2. Is everything matched up? Is everything matched up? It is. You give me any number that's an integer, it's here somewhere, right? 1 minus 1, 2 minus 2. Everything is in there, and everything's matched, paired up with one and only one number. So, the size of n is equal to the size of z. Maybe you'd say, I said something earlier about hotels, we could say, imagine you have an infinite hotel. Maybe let's call this hotel infinity. Suppose you have an infinite hotel, and it's full. Someone comes knocking on the door and says, you got a room? Remember, in a finite hotel, what could we say? Full, nothing I can do. But an infinite hotel, assuming you have compliant guests, suppose one person comes, what do you tell them? What do you do to solve the problem? You wake up everybody, tell everyone if you're in room n, go to room n plus 1, and the first room will be empty. You say, if a hotel with infinite number of rooms is full and a guest comes, what can you do? Say a new guest. Then, what can you do? You want to fill can you solve the problem? We just said, no problem. What do? Send every guest in room n to room n plus 1.
Did you write there if a hotel with infinite number of rooms is full of new and guests come?
And a new guest comes. I guess we should straighten it out for the archive. And a new guest comes. What can you do? So you can see, you had your hotel room, maybe guest 1, guest 2, guest 3, room 1, 2. All right? We could say each room has a number. We're saying let's say we have enough number of rooms, it's 1, 2, 3, 4, 5, etc. Then you can just do this, just say, leave this room empty, this is room 1. X1 went to room 2. X2 went to room 3, etc. No problem. So, okay, what happens if, maybe it's the same story. What if everyone got that? So I'm going to not rewrite this. So we have no problem. If we have a hotel which is infinite, and one new guest comes, we want to accommodate them. We just wake up everybody up. If you're in room n, go to room n plus 1. First room will be empty. All right, what happens if, suppose we have the same problem. Suppose you have your same hotel, you're the gatekeeper, the front desk, and now k guests come. What does that mean? 1, 2, 3, 4, 5, 6, 7. Could be 2, 3, could be 5. Can you still solve the problem? Can you solve the problem? Yeah.
So could you do the same thing, but instead of n plus 1, you do like n plus k?
Exactly. So again, we'll say, good, so no problem. Here we have room 1, room 2, x1, x2, and we send x1 to room, goes to 7, to room n plus 1. Sorry, k plus 1, right? Then what's going to happen? then I'm gonna have rooms 1, 2, 3, 4, up to K empty. And room K plus 1 is guy X1. And room 2, I guess I should say something. When I say guy, I'm not thinking gender. When I say you guys, I'm not ignoring it. I just got used to that. Some people say, what are you? This is for all the people on YouTube listening to. So here, all right, well, when should there be a problem? Well, suppose we do this and an infinite number, maybe we'll say the size is n. Guests. Then is there a problem? Harder, but it's similar to the one that we wrote before. Again, this is no problem. Maybe it seems harder because here, we can't just say, oh, tell the first guy to go to room 1 plus K or something. Because we have an infinite number of guests. We have, or at least the same number of guests as there are natural numbers. What do? We send X1 to room 2. Send X2 to room 4. This guy to room 6. You see what's happening? So here we have, maybe here's our original arrangement, X1, X2, X3. It's room 1, 2, 3. This guy's going to leave room 1 blank. He'll go to room 2. This will leave room 3 blank, and we'll have X2. Question or comment?
When you erased it, so
Say again. So you
oh no,
understand.
you went with the K plus 1, 1. I just wanted to look over.
Yeah, I mean, just think of it this way. Like, I'm using more notation than some people could. Here I'm saying, like, suppose I had X1 in room 1, X2 in room 2. And then I have my K guests, 1, 2, let's just call them 1, 2, 3, 4, 5, K. What am I gonna do? I want my first K rooms empty. I'll make them empty, 1, 2, 3, K. And here I'll put X1 in room K plus 1. X2 in room K plus 2. And then, we have room for our new guests. I'm going to say G1 goes here, G2 goes here for guest 1, guest 2, guest K. Good? So here maybe you're thinking, well, let's finish this. So here, and now what? Here I could put, I don't know, guest 1, guest 2. Because all the odd number spaces are unoccupied, and I can just put the new guests in the odd spaces, the even spaces where the previous guests filled. So maybe now you're thinking, oh, is that why? All these sets have the same size? Is that why we don't have another word for infinity? Because all the infinities are the same? Maybe you even say, what's the story with Q? Let's list Q. Maybe we'll list Q. What's the name of this class? What was the name of this class we just finished? Don't say 310. Linear algebra. What did we talk about in linear algebra? What was one of the big things? Matrices. So I can write Q in a matrix. I could say, all right, Q is like 0, 1, minus 1, 2, minus 2. Maybe I could put a half, minus a half, a fourth, minus a fourth, a third, minus a third, etc. And I can get everything, right? That's everything. You may think about what's the next one. I'll write 1/5 minus 1/5. I'll get it. Good? So now, you could say, well, does this really have the same size as the first one? Or the same size as the natural numbers? Well, I call this one number 1. Call that 1, call that 2. I don't want to go all the way across, I'll never get there, right? Because then everything below this line will get paired. Maybe I'll call this the 3rd one. I'll call this the 4th one, the 5th one, the 6th one. And forget about the numbers. Here we can say if I have A11, A12, A13, dot, 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 21, A22, A23, dot, 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 dot. I could pair them. Maybe I could say, I could pair this with 1. I could pair this with 2. I could pair this with 3. And I have to kind of zigzag up and down, because if I just went all the way across or all the way down, I'd never get there, right? But if I do this, maybe I'll say here A31, I'd associate that with 4, and then go across. Associate this with 5 and 6. So, everything is paired with 1 and 1 number, right? So if I have a matrix whose width and length is infinite, or whose size is the same as the natural numbers, then that set is also infinite.
Isn't that how they create neural networks?
Oh, I don't know.
It's basically, they do the same way by pairing two.
Maybe, like, I don't know. Like, what I've heard about neural networks, because I've only heard about neural networks in terms of like trying to teach computers how to play games, is, you know, they give it the rules, sometimes they'll even give it that, and it plays itself.
Yeah, that's
Which
how
is it?
They create it with matrices, and they kind of like bond them so that one output creates another reaction, which creates another one. It kind of like ties them all together.
So here, so as a result of this, we could say this thing has the same size as the natural numbers. They have a word for this. Maybe we say if a set A has the same size as n, there's a definition. And what do we mean by that? That is, there is a one-to-one function, one-to-one onto function from A to, I guess we always use n as the domain, so it doesn't matter, to A. Then we say A is countable. So here, how many people take calculus 2? So, well, here's something maybe you might know, remember from calculus 2, but something I always say, you don't need to know calc 2 to do this. What is 1/2 plus 1/4 plus 1/8 plus 1/16? You may say, how am I supposed to know? Well, think about what's happening. Someone gives you half the pie, plus 1/4 of the pie, plus 1/8 of the pie, plus 1/16 of the pie. What's that? All together, what is it giving you?
1.
1. You may have learned this actually before calculus 2, actually, because this is a geometric series. This is a geometric series with ratio less than 1 in absolute value, so it converges. Remember? Because I've seen variants of this taught in other classes, which were way before calculus. So this is a useful fact, and we'll use this. Maybe we could say, what is the size of a countable set? Well, maybe we could say, if we can cover a set by n arbitrarily then we'll say the set has length. Make sense? Like there's someone said, oh, I have to paint this room. And someone said, oh, I can do it with a small amount of paint. Someone said, I can do it even smaller. Even smaller. Then you say, you know, you need paint this. Or you'd say you need zero amount of paint to do it. So this is the idea. So now we can say, all right, if you claim any countable set has length 0. Say length because I'm being a little loose. Maybe say that is for any number, people like to use this letter, is it epsilon? For any number epsilon, there is a set. Let's say S sub epsilon with, let's give this a name, A, where A is a subset of S sub epsilon. And the size of S sub epsilon is less than epsilon. Still with me? I'll explain. So here, maybe we'll say, maybe let's take our countable set. Our countable set was called A. We'll call it A1, A2, and we want to say this has small size, so what are we going to do? Maybe we'll draw a little map of our set. Here's A1. We'll cover A1 by an interval with length epsilon over 2. In particular, we'll say A minus epsilon over 4, comma A plus epsilon over 4. We should write it this way so we can write it. Okay. By interval of length. Epsilon 2. That is cover A1 plus. Do we know what this means? Or do you like pre-calculus less than? What does this mean? This means an interval starting all the points which are bigger than this and smaller than this, right? Like if I was to say, what's 0, 1? That's all the numbers between 0 and 1, not included. Some people like to write circular dots. Open circles. Remember? So that's what I'm saying here. I'm going to say, here's A1, I'm going to cover it with an interval of length, epsilon over 2. I want to continue this pattern. I'm going to cover A2 by A2 minus, I need to cut the length, so this is going to be epsilon over 8, comma, A2 plus epsilon over 8. What's the length of this set? This one had length epsilon over 2, 2 times epsilon over 4. This one is epsilon over 4, right? Basically the idea is I'm covering this with an interval of length epsilon over 2. Maybe I have A2 here. I'm covering this with an interval of length epsilon over 4. Good? No good? Now, Well, I'll continue. What am I going to cover A3 by? Well, I'll be A3 minus something, A3 plus something. I think that's plus epsilon over 16, epsilon over 16. All these are centered at our point AN. And now we can say, well, I've overcovered my set, right? It's like there's a little overspread, right? Because I didn't just cover the set, I covered a little more, right? Like when I covered A1, I got a little more than A1. When I covered A2, I covered a little more than A2. So maybe we could say, what's the size of my covering set? So the size of my covering set, we call it S of epsilon, is less than or equal to. Why am I saying less than or equal to? Because it could be overlap. So it should be less than or equal to the size of my first set, A minus epsilon over 4, A plus epsilon over 4. So the size of each individual set. Good?
So in the scale you're telling for A1 is that E over 2. But down you're saying that it's covering A1 by A minus 1, 2, and E over 4.
Yes. Remember, what's the length of it? If I give you an interval, what's the length of this interval? What? If I have 1 and 3, what's the length of this? What?
Square root 5?
No. This isn't a vector. This is the interval.
Okay. It's 2.
This is the interval. So the length of this is just what? It's 3 minus 1.
2.
So here, what's the length of this? The A1's cancel. I get epsilon over 4 minus epsilon over 2. Maybe you could say has length epsilon over 2 has length epsilon over 4. So that's how we're gonna. So I'm gonna write some dots. So this is less than or equal to epsilon over 2 plus epsilon over 4 plus. And we actually get what? Epsilon times our geometric series. Epsilon times 1/2 plus 1/4 plus 1/8. I don't know why I thought about this, but one student told me this joke. Oh, a guy walks into a bar and says, "Can I have a beer?" His friend comes in, "Can I have a quarter of a beer?" The guy says, "Can I have an eighth of a beer?" The bartender just pours out a beer. He said, "You guys are testing my limits." Ha ha ha. It was someone else's joke, not mine. So here, so what's the punchline? So my set A has to have length 0. Because no matter how, I can always pick epsilon to be as small as I want. So the size of A has to equal 0. Maybe it's less than epsilon for any epsilon or size of A. Yes.
What's that? Is it less than or equal to 2? So size of A is less than or equal to.
It's not.
Oh.
Epsilon.
How do you spell that? Can you write it on the board?
This is one of the letters in the Greek alphabet. Maybe you'll feel this way, but I think by the time I was a third-year student, if you take enough math and physics classes, you will know the entire Greek alphabet. Remember, the first time I saw a Greek newspaper, I was like, wow, it's like math. But it doesn't make any sense, because they're not writing equations. All those letters, they have a pronunciation like all the letters in our alphabet. So they're making words without thinking math. But yeah, alpha, beta, gamma, delta, epsilon, delta. Oh, I said delta. seen them, or, you know, you've taken math classes, you've taken physics classes, you've seen them all over the place. I mean, I guess that they have a very special meaning, like pi means the ratio of the circumference of the circle to the radius. Rho means the density usually. Maybe you could say mu is the mean, sigma is the standard deviation. But these are all in particular contexts. But really, like to a Greek person, pi is like the letter P. Alpha is like the letter A to us. So, anyway. So these absolutely, I could have used E, but like, you know, classically they like to write this. So here, what are we saying? So the big deal about all of this and this argument is to show if I have a countable set, it has to have length 0 or measure 0. It can be squeezed into a set of arbitrarily small length. Because no matter how small you want it to be, I can make cover the first set with something half the size, something with a quarter the size, eighth the size. I have enough. I can squeeze it into an arbitrarily small set. Well, remember, there's one set, which was on our list. There's actually what we could say. So now we could say, what we have said, so far, we have the size of n is equal to the size of n union 0. You could say union more, which is equal to the size of q, which was quite impressive. It was kind of impressive because q feels like it's all over the place. It feels much bigger than the integers. But q, we said, you know, basically what a countable union of countable sets, which is what we kind of proved for q here, is also countable. We also said it was z. I should have done that first. But the size of 0, 1 is strictly bigger than n. Why? Because I can't squeeze 0, 1 into a set of size less than 1. Right? By this argument here, I did all this to say, like, you know, so 0, 1. Bigger. We can say because the size of 0, 1. I shouldn't say the size, I should say the length. Because the length of 0, 1 is equal to 1. Any countable set has to have length arbitrarily small. Good? No good? I can tell you the standard argument. I didn't do the standard argument. But this, I think, is much nicer. Maybe there's another argument. This will be the more famous argument. Maybe say alternatively. If there was a pairing, if there was a one-to-one pairing between, say, 0, 1, and, let's say n, what would it look like? I would have 1, 2, 3, maybe there's my domain. First thing I have 0, alpha 1, alpha 1, 2, alpha 1, 3, etc. There's my first argument. So here's another argument. I think this is a great argument. But maybe it's not one, you know, most people would think of. But this is something, I always think about this, like in terms of like the work you have to do. Suppose you have a job to do, oh, you want to clean your room. It seems like too much. Well, I'll clean half of it today. The next day, it's like, that was too much. I'll do half of what I did yesterday. And then I'll have to do half of that the next day. You'll never finish, right? Maybe this is very pessimistic thinking. But I think about things like that. If you can keep this what? If you have what? If you make it so you won't keep on cutting in half, you'll finish your job. Because some people say if you do a little bit a day, you'll finish. That's not true. I feel like doing something else. Remember someone said, oh, a bird in the hand is worth 2 in the bush. No, it's not. Depends on the probability of you catching the 2 in the bush, right? If you're very good, the 2 in the bush might be worth more. Guess what we do? So anyway, like someone else told me, better safe than sorry. don't know, it depends on how much you pay to be safe, right? All right, so here's the second argument. We haven't finished it, but this is the beginning of it. If there's a one-to-one pairing, it would look something like this, right? I'd attach, maybe have a first one, some number in 0, 1. I have a second one. Alpha 2, 1, alpha 2, 2, alpha 2, 3. And I keep going, right? Alpha 3, 1. So supposedly that should be a complete list. So here, let's create the number. Maybe we'll say let beta II equal to alpha II plus 5 if this is less than 1. I mean, if this is less than 9. So create a number. 0 times B11, not times, A, 0 dot B11, B22. So, how am I going to make this? How do I make B11? Take A11, add 5 to it, if that's less than 10. Otherwise, subtract 5 to it. So I'm going to get a new, so now I'm going to say, what's the punchline of all of this? But 0, B11, B22, etc. is not on the list. It's not one of these numbers. Why is it not one of these numbers? It's not the first one, it disagrees in the first place. It's not the second, it disagrees in the second place. And you can keep going. So it's not on the list. So no matter what list you make, you can always create a number not on the list. You can create a whole bunch more, but that's one. So no matter what list or no matter what pairing you attempt to make from the natural numbers to 0, 1, you're going to miss at least one. Or you're going to say any function from the natural numbers to 0, 1 is not onto from the language we used in a previous class. But we talked about onto in this class, right? So there you have it. There are big, not all infinite sets have the same size. We could say 0, 1, which doesn't seem that much, seems kind of small in comparison to some of these other sets. Actually, is the biggest of our basic infinite sets, of the ones maybe we're most familiar with. And we could do a little work to say that 0, 1 cross 0, 1 has the same size as 0, 1, and stuff. So I'll end with, I should be careful because my guitar is cold and fingers are cold. But I remember I said in the beginning, what did I say? There's 3 kinds of mathematicians. Ones who know how to count and ones who don't. And I'll tell you a story.
And now it's time for Silly Songs with
Nader Gubrin.
the part of the show where
Nader Gubrin.
comes out and sings a silly song. So without further ado, Silly Songs with
Nader Gubrin.
I played this for you in the last talk. But I was playing this one. Oh, let me do a warm-up piece for 1 second. I have 5 minutes or so? 3 minutes? I know, you're getting impatient. Maybe close enough. So I played this piece. And when I got to this part, I was playing it wrong. I was playing it in front of some friends of mine, and they're like, dude, it's in 3. And I was like, I just heard it. I just played it without hearing it. And because when you have music, you have a certain amount of time. So I was playing it in 4/4, which is really hard for me to do now because once that guy did it, I was like, I need to straighten this out. Because really, was like I would count 1, 2, 3, 4, 2, 3, 1, 1, 2, 3. It's funny because when I play music, people say, you're a mathematician. How can you be messing this up? I was like, when I play music, I don't count very much. It just goes like this, where I feel it. And only in some parts where I know I have a good chance of making a mistake will I count 1, 2, 3. So, questions or comments?
This has been Silly Songs with
Nader Gubrin.
Tune in next time to hear
Nader Gubrin.
sing.
So thank you for coming to this talk. I hope you enjoyed it.